Hi, welcome all to the online classes. I'm Mukesh Bhardwaj. Today going to teach a topic, the nature and the propagation of light in physics, BTech first semester engineering. So, the nature and propagation of light. To understand light rays and wavefronts by this topic or by go through this topic, we understand the light rays and the wavefronts. To analyze reflection and refraction of light, to understand total internal reflection, to analyze the polarization of light, to use Huygens principle to analyze reflection and refraction. Introduction: why does a rainbow of colors appears when these tools are placed between polarizing filters? Our study of light will help us understand why the sky is blue and why we sometimes see a mirage in the desert. Huygens principle will connect the ray and wave models of light. The nature of light. Light has a property of both waves and particles. The wave model is easier for explaining a propagation, but some other behavior requires the particle model. The rays are perpendicular to the wavefronts. See figure at the right. So when wavefronts are spherical, the rays radiate from the center of the sphere. When wavefronts are planar, the rays are perpendicular to the wavefronts and parallel to each other. Reflection and refraction. As you're observing this figure, the light is both reflected and refracted by the window. Plane waves reflected and refracted from a window. Woman sees reflected image of hat outside the window, incident wave. Man see refracted image of hat. So this is the reflected wave for the woman, and the man sees the refracted image of hat, as the hat is from the outside the screen and its image get reflect and refract both. Okay, so the waves in the outside air and glass represented by the rays in figure B, incident rays, reflected rays and refracted rays. The representation simplified to show just one set of rays, incident, reflected and refracted, and the normal to all these coincide of these three rays, and the line parallel to the, or just we can say the x-axis crossing this line is known as the normal. Specular and diffuse reflection. Specular reflection occurs at very smooth surface, left figure. Diffuse reflection occurs at rough surface, right figure. Our primary concern is with the specular reflection. So whatever the reflection takes place at very smooth surface, it is known as specular reflection, and the reflection takes place due to the rough surface is known as the diffuse reflection. Laws of reflection and refraction. The incident reflected and refracted rays and the normal of the surface lie all in the same plane. As shown in the figure, when a monochromatic light ray crosses the interference between two given materials A and B, the angles theta A and theta B are reflected related to the index of refraction of A and B by sin theta A by sin theta B equals to NB by NA. The frequency does not change on passing through a surface, but velocity does, and so wavelength. The index of refraction the angle. Snell's laws applies in material. Lambda equals to lambda naught by n. Figure 33.7 right illustrates the laws of reflection and refraction. Reflection and refraction in three cases. If NB is greater than NA, the refracted ray is bent towards the normal. If NB is less than NA, the refracted ray is bent away from the normal. A ray oriented along the normal never bends. So it's depend upon the incidence angle. A ray entering a material of larger index of refraction bends towards the normal. A ray entering a material smaller index, the refractive index, that is the particular characteristic of a material. So the bending of the light or the refracted light or the reflected light depends upon the refractive material or the indices of the refractive material. Why does the ruler appear to be bent? The straight ruler in a figure appears to be bent at the surface of the water. Shows why. So as you just see that a straight ruler half immersed in water just feel or look like that it is bent towards somewhat upper side. Just why it is so? Because the refractive index of air is 1 and the refractive index of water is 1.33. So that's why it is moving towards or bent towards the or to the normal, away from the normal. So that's why it is appear in position of the end of the ruler. Actual quasar light, image light, and this is there. These are the some indexes of refraction for some materials in a tabular form. You just go through it. Read problem, solving strategy. Example 33, find the angles of reflection theta and the refraction theta b using the figure below. So use the formulation, get the solution for the following problems. Light striking at critical, the total internal reflection. Light striking at the critical angle emerges tangent to the surface. If theta is greater than theta critical, the light is undergoes total internal reflection. Na sin theta A equals to Nb sin theta B equals to Nb for total internal reflection. Theta critical is sin inverse Nb by Na. Some application of total internal reflection, fiber optics. The light is trapped in the rod if all the angle of incidence such as alpha, beta and gamma exceed the critical angle. Total internal reflection in a poroprism. Binoculars use poroprisms to reflect the light to each eyepiece. A binocular using poroprism below and a light pipe right make use of total internal refraction in their design. Can the above work if the outside of the rod is air? How does it the optical fiber works? Diamond and a periscope. Diamonds sparkle because they are cut, so the total internal reflection occurs in their back surface. Example, leaky crown glass periscope. Why will periscope no longer work if one arm of prism is in water? Dispersion, the index of diffraction depends on the wavelength of the light. The dispersion by the prism. The index of refraction, silicate flint glass, borate flint glass quartz, silicate crown glass, fused quartz. The formation of rainbow is due to the combined effects of dispersion, refraction and reflection. The path of the light rays entering the upper half of the raindrop. This is the raindrop. And this, the pattern of the rays entering the lower half of the drop, not shown, is the same but flipped upward down. Forming a rainbow, the sun is in the illustration is directly behind the observer at P. So total internal reflection takes place. Polarization electromagnetic wave is linearly polarized if the electric field has only one component. Figure shows the right shows a polarized and polarizing filter. Polarizer figure shows a polarizer and an analyzer. A polarizer reduces the intensity of unpolarized light by factor of 2, so the intensity of transmitted light is I naught by 2. Second polarizer at angle phi relative to the force further reduce the intensity according to the Malus law, I equals to I max cos square phi. When light is reflected at the polarizing angle theta p, Brewster angle, the reflected light is linearly polarized. The polarizing angle theta p is when the reflected and refracted rays are 90 degrees from each other. Just go through this figure. Using figure, we just get some conclusion. The reflected, refracted, and the fully polarized and partially polarized lights in the daytime and the night time. Circular polarization results from the superposition of two perpendicular uh, polarized electromagnetic waves having equal amplitude but a quarter cycle phase difference. The result is that the electric field vector has constant amplitude but rotates about the direction of propagation. Scattering occurs when light has been absorbed by molecules and re-radiated. Below show the effect of scattering for two observers. Why are clouds white? Clouds are white because they scatter all wavelengths efficiently. Huygens principles. Every point of a wavefront can be considered to be a source of secondary wavelet that spread out in all directions with a speed equal to the speed of propagation of the wave. In figure, Huygens principle can be used to derive the law of reflection. Huygens principle can be used to derive the law of refraction. Huygens principle, a mirage, a principle can also explain the formation of mirage. A mirage figure shown below. The hot air near just a hot air near ground has a smaller end than cooler air higher up. Largest radii wave fronts travel, approximately start, and the mirage forms. T minus alpha 1 and E2 equals to E naught 2 sine omega t minus alpha 2, where omega is equals to 2 pi nu or 2 pi nu, or nu is the frequency of the wave, where k is equals to 2 pi by lambda, and lambda is the wavelength of the wave. From the superposition principle, the resultant disturbance can be added up algebraically. E is equals to E1 plus E2, and by substituting the values of E1 and E2 by the use of superposition principle, finally we get some equation, and it is come out to be E equals to A sine omega t cos theta minus A cos omega t sine theta, and which is also can be written as E equals to A sine omega t minus theta. This equation represents the resultant wave produced by the superposition of two waves. Its amplitude is A and phase angle is theta. Squaring and adding both the equations, almost we get an amplitude, and it is come out to be k delta minus phi k delta minus 5. Yes. So this is the principle of superposition. Now I'll let you know some. Just wait a minute. So the Huygens principle and the law of refraction. Just wait a minute. There's some disturbance in the. Sorry for the disturbance. Yes, Huygens principle, the law of refraction. Huygens principle can also explain the law of refraction. As the wavelet propagates from each point, they propagate more slowly in the medium of higher index of refraction. This leads to a band in the wavefront and therefore in the ray. Now, I just want to give some brief introduction about the incoherent and coherent sources which are to be used for producing the interference. So, because I am using the word, what do you mean by the coherent source? And coherent source are to be taken, and by using the Young's double slit experiment, we had already checked out this coherent source produce the wavefronts, and these wavefronts generate the secondary wave. Emission of light, radiation from each light source is the transition of a very large number of atoms from the excited state to the ground state. After receiving energy, atoms remains in the excited state for about 10 to the power minus 8 seconds and then return back to the ground state. No correlation of phase is found in the radiation emitted from these atoms because the process of emission of radiation from the atoms is random. If we take two independent light sources, the phase difference between the waves emitted by these sources will not remain constant in time but will vary at random. Thus, the light sources are said to be incoherent if there is no definite phase relation between the waves emitted by the sources. That is, the phase difference between the waves vary with time, are known as incoherent source of. Emitted by the incoherent source will not be stable because sometimes these waves will satisfy the condition of constructive interference. Uh, so the interference pattern obtained from the waves emitted by the incoherent sources will not be stable because sometimes these waves will uh, satisfy the condition of constructive interference and other times they will satisfy the condition of destructive interference. The change of intensity in interference pattern will be so rapid that one cannot see the interference. When the phase difference between the between the waves received at any place from a light two light source does not change with time, that is, it remains constant, then these sources are called coherent sources. In that case, the interference pattern will be stable and one can see the interference. In actual practice, it is not possible to have two independent sources which are coherent. If we construct two sources from one light source by any means, then whatever change occurs in the phase of the wave produced at any instant from one source, the same change will occur in the phase of the wave produced at the same instant from the another source. In this way, the phase difference between the waves produced by the both source remains constant. Thus, from the superposition of waves produced by two coherent sources, a stable interference pattern can be obtained. There are two types of coherence. One is the temporal coherence and the coherence in time, and the second is the spatial coherence, that is coherence in the space. So, if I'm just give you the brief introduction about the temporal coherence, when a light waves of fixed frequency are emitted from a light source, it is said to be monochromatic source, which we had already discussed. What do you mean by the monochromatic source? Such type of light wave can be represented by an infinitely long sinusoidal wave and its frequency spectrum I had already discussed in the previous slides. Practically, light waves are emitted from the source when the electrons in the higher excited state transit to the lower or ground state. The duration of this transition is about 10 to the power minus 9 seconds. The sine wave character of the emitted wave does not extend to infinite time, but only for this limited time. So, next. So the Huygens principle can also explain the law of refraction. As the wavelets propagate from each point, they propagate more slowly in the medium of higher index of refraction. This leads to the band in the wavefront and therefore in the ray. So Huygens, the frequency of the light does not change, but the wavelength does as it travels into a new medium. And we just get the relationship through the help of Snell's law. Huygens principle. So highway mirages are due to the gradually changing index of the refraction in heated air. So this is the phenomena how the mirage appears to be seen on the highways in the sunny hot days. So this is the youngest double slit experiment which we had discussed. Just have a look for this. We just take a cardboard in which we had just made two slits, S1 and S2, and the monochromatic source of light is, that is sun rays, are we just incident on that cardboard, and the viewing screen particle theory prediction, viewing screen actual. So what we are just observe and what we are just get. So that fringes obtained actual are known as the fringes, interference of the light in a constructive and destructive manner. So, just wait a minute. So the condition for sustained interference, there are certain conditions for sustained interference which are very important. The condition for sustained interference are the wavelength or frequency of the interference wave produced by the light source must be same. They are very same, the wavelength or the frequency of the interfering light. The light sources must be coherent. That is, the phase difference of the wave emitted by them must be constant with respect to time. The interference or interfering waves produced by both the sources should propagate almost in the same direction. The amplitude of the wave should be nearly equal so that the fringes may appear clear and distinct. If there should be good contrast between the fringes. If interfering waves are polarized, then polarization state of both waves should be same. The path difference between the waves should not be very large compared to the wavelength. The path difference should not be very large compared to the wavelength of the light. So, and we are just know that practically coherent sources are not possible, but we are need to produce the coherent sources. So there are two methods of producing the coherent sources. First is by the division of the wavefront, or second is by the division of the amplitude. So for the interference of light, coherent sources are produced by first, that is division of wavefront. In this method, the incident wavefront is divided into two parts, and these divided wavefronts, after traveling or after traveling different optical paths, are made to superimpose at very small angle. This produces interference fringes. These two parts of the wavefront are equivalent to the wavefront produced by the two virtual coherent sources. For this method, it is required that the light source should be narrow or a point source. This method is used in Young's double slit experiment and Fresnel's biprism experiment. Second method for producing the coherent source is the division of amplitude. In this method, the amplitude of the incident wave is divided into two or more parts by partial reflection or refraction, and these divided parts are made to superimpose by spatial arrangement. This produces interference fringes. For this method, it is required that the source should be a broad source. Interference fringes are produced in thin films. Newton's ring experiment and Michelson interferometer by this method. So, next, the interference occurs because each point on the screen is not same distance from both the slits. Depending on the path length difference, the wave can interfere in constructively bright or destructively dark spots. So this is the physics or the equation related to the interference pattern, constructive interference and destructive interference, depending upon their phase and the frequency. Between the maximum and the minima, the amplitudes vary smoothly. Since the position of maxima except the center one depends on the wavelength, the first and the higher order fringes can have a spectrum of colors. So Fresnel biprism is an experiment in which two coherent sources are obtained by refraction from Fresnel biprism. It consists of two small prisms placed base to base, placed to base. Their refractive angles are equal and very small, of order of 1/2 degree. Or in fact, biprism is made out of a single piece of glass by grinding and polishing. By grinding and polishing. So, in order to obtain interference fringes, a vertical narrow slit S is illuminated with a monochromatic light produced by a sodium lamp. Biprism is placed in front of the slit as in such a way that the middle edge of the biprism remains parallel to the slit. The slit is perpendicular to the paper in the previous figures. When a cylindrical wavefront emitted by the source as is incident on the refractive surfaces AB and BC, half of the wavefront is reflected by AB and rest half of the wavefront is reflected by BC. The refracted rays appear coming from S1 and S2, that is slits. In this way, the two virtual images are formed. In the overlapping region of the light diverging from the slits, interference fringes are formed. As a result, interference fringes of equal widths are observed in this region. These fringes can be seen with the help of eyepiece. So, this is almost where we had covered everything related to the interference Now, there are some more definition which we need to discuss about the or for the interference fringes produced by the white light. White light has several colors whose wavelengths vary from 4,000 angstrom to 7,000 angstrom. When the slit of biprism is illuminated with white light, two coherent virtual sources S1 and S2 are produced after refraction from the biprism. Interference patterns are formed on the screen for all wavelengths. The fringe widths are different for different colors. Thus, the interference pattern on the screen will have the following characteristics. Uh, Central fringe, fringe of zero order of interference pattern is always white, which is shown in the figure. Which is shown in the figure. All the waves of different colors coming from slits reach the center with the same phase. Thus, the bright fringes due to all colors will overlap at the center and will produce the fringe of white color. Outer edge of dark fringe is found violet and inner edge is found red. Smaller number of colored fringes are seen. A uniform illumination is observed at the place of fringes of high order because there is overlapping of waves of different colors in that region. Fringe width is non-uniform. Now, there is a determination of thickness, that is refractive index of thin transparent film by biprism. So, when a thin transparent film or thickness T of the refractive index mu is placed in the path of secondary wavelets coming either from the sources S1 and S2. So, this is some mathematical relation will take place for calculating the thickness and all that. I'll show in the next slide. So wait a minute. So this is I had already discussed with you the visible spectrum. The index of refraction of material varies somewhat with the wavelength of light. Now we are going to start with interference in thin films. No, if the interference in thin films, when the light is incident on the thin films, such as oil layer or on water, then the thin mica sheet or a soap bubble, light is uh, reflected and refracted from the upper and lower surfaces of film. These light rays, when made to interact each other, produce interference pattern. Light of different wavelengths produces different interference fringes. The dispersion of white light from this thin transparent film is due to the interference phenomena. And there are some important points like complementary interference is one word over there. So, complementary, the condition of maximum minima is reflected light source are just reverse of those in transmitted light. Hence, if the upper surface of the film appears bright in monochromatic reflected light, then the lower source surface of film will then appear dark in transmitted light and vice versa. Thus, one can say that interference in reflected light is complementary to interference in transmitted light. So, interference in ultra thin transparent film, when the monochromatic light is incident on ultra thin transparent film, That is, the time is very, very less than the wavelength, then the change in the phase is equals to zero. In this case, it will satisfy the condition of destructive interference, and hence the film will appear dark in the reflected light. But in transmitted light, the film will appear bright as above conditions satisfy the condition of constructive interference. So transparent film in white light, when the white light is incident on the transparent film, some wavelengths of white light may satisfy the condition of destructive interference, and hence these wavelengths of colors will be missing and other wavelengths will be present. The colors which are present depend upon the thickness of the film and the angle of incidence, and form their own interference pattern. Thus, we see colors in thin film. Now, the types of fringes exhibited in thin film. Generally, there are two types of fringes appeared in the thin film. Uh, Fringes of equal inclination and fringes of equal thickness. So when a monochromatic light of wavelength lambda is incident on a transparent film of constant thickness, the fringes are the locus of all points where the angle of incidence is same. Where the angle of incidence is same. Such fringes are called fringes originating from the same inclination on the film. Such type of fringes are observed in Michelson interferometer. And fringes of equal thickness, when a monochromatic light of wavelength lambda is incident on a transparent film of very varying thickness, that is non-uniform thickness, the fringes are the locus of all the points where the thickness of the film is same. Such fringes are called Fizeau fringes or fringes of equal thickness. Next. Just wait a minute. Now, the diffraction by a single slit or a disc. The light will also diffract around a single slit or obstacle. So, if you place an obstacle in front of sound source, sound is always heard behind the obstacle. Uh, it is possible only when the sound waves bend around the corners of the obstacle and reach the listener. The phenomenon of bending of the sound wave around the corners of the obstacle is called diffraction of sound. So, similarly, the outer boundary of the shadow of an obstacle formed by light is not sharp but blurred because some part of the light bends around the corners of the end and enters into the geometrical shadow region. Uh, if we see a vertical tube light through a parallel narrow slit made between two fringes capped in front of eyes, alternate light, bright and dark fringes are seen. Both these events can be explained on the basis of diffraction of waves. Another example of diffraction of waves is the reception of radio signals by different receivers. Thus, the event of banding of waves around the corners of an obstacle, that is diffraction, is general property of the wave. The phenomena can be observed very clearly in the sound waves and radio waves, but rarely observed in the light waves. In special cases, when the obstacle is very small, this event can also be observed in the light. The phenomenon bending of light waves around the obstacle and entering into the region of the geometrical shadow of the obstacle is called diffraction of light. So, diffraction of light is observed only at the boundary of the geometrical shadow. In short, the phenomena of a deviation of light from its rectilinear propagation is called diffraction. The diffraction phenomena was first discovered by Grimaldi in 1665, but correct explanation of this phenomena was given by Fresnel in 1818 on the basis of Huygens wave theory. So, dependence of the diffraction of waves on the size of the obstacle and wavelength of the waves on the following parameters: size of the obstacle, wavelength of the waves. So, now I would like to some light on the difference between the interference and the diffraction. Interference is due to the superposition of waves, that is, two or more but finite in numbers emitted from the monochromatic coherent sources. And the diffraction is due to the superposition of secondary wavelets emitted from different points, infinite numbers of the same wavefront. In an interference pattern, the minima are usually almost perfectly dark. In the diffraction pattern, the minima are not usually dark. In an interference pattern, all the bright fringes are usually of same intensity. And in the diffraction pattern, the intensity of bright fringes decreases as the order of fringe increases. The interference fringes may or may not be equally spaced. The diffraction fringes are never equally spaced. In general, the number of observed interference fringes is quite large, and in diffraction, the number of observed diffraction fringes is quite small. And the diffraction are of two types: Fresnel and Fraunhofer diffractions. Fresnel and Fraunhofer diffraction. So there is a difference between the Fresnel and Fraunhofer diffraction. I would like to just give a small introduction between the difference between the Fraunhofer and Fresnel diffraction. In Fresnel diffraction, the source of light or observation point are both at finite distance from the diffractor, whereas in Fraunhofer diffraction, the source of light and observations point both are effectively at infinite distance from the diffractor. The incident and diffracted wavefronts are either spherical or cylindrical. The incident and diffracted wavefronts are plane in Fraunhofer diffraction. In Fresnel diffraction, no lens or mirror is used. Whereas in Fraunhofer diffraction, diffracted light is collected by lens. In Fresnel diffraction, distance are important in this class of diffraction, whereas in Fraunhofer diffraction, angular inclinations are important uh, in the case class of diffraction. In Fresnel diffraction, the diffraction pattern is shadow of the diffracting element modified by the diffraction effects. In Fraunhofer diffraction, the diffraction pattern is an image of the source modified by the diffraction at the diffracting element. In Fresnel diffraction, the center of the diffraction patterns may be bright and dark depending upon the number of Fresnel's half-period zones. Whereas in Fraunhofer diffraction, the center of the diffraction pattern is always bright for all rays parallel to the axis of the lens. So, next. So, diffraction by a single slit or disk, the resulting pattern of light and dark strips is called diffraction pattern. This pattern arises because different points along a slit create wavelets that interfere with each other just as a double slit would. Next. The minima of the single slit diffraction occur when d sine theta equals to m lambda, where m is equals to plus minus 1, 2, 3, and so on. Diffraction grating. Uh, Diffraction grating consists of large number of equally spaced narrow slits or lines. A transmission grating has slits, while a reflection grating has lines that reflect light. The more lines or slits there are, uh, the narrower the maximum of the diffraction pattern are defined by sine theta equals to m lambda by d, and these are the fringes obtained. The spectrometry and spectroscopy. A spectrometer makes accurate measurement of wavelength using diffraction grating or prism. So, next, the spectrometer makes an accurate measurement of the wavelengths using a diffraction grating or prism. The spectrometer and spectroscopy. The wavelength can be determined to high accuracy by measuring the angle at which the light is diffracted. The wavelength is given as d by m sine theta. Atoms and molecules can be identified when they are in the thin gas through their characteristic emission lines. Interference in thin films. Another way path lengths can differ and waves uh, interfere is if the travel through the different media. If there is a very thin film of material, a few wavelength thick light will reflect from both the bottom, top of the layer, causing interference. This can be seen in the soap bubbles and oil slicks, for example. Interference in thin films, the wavelength of light will be different in the oil and in the other, and the reflection at point A and B may or may not involve the reflection. Interference in thin films we had already discussed. Similar effect takes place when a shallowly curved piece of glass is placed uh, the above concentrated appears. We can also create a thin films of air by creating a wedge-shaped gap between two pieces of glass. Now, interference in thin films. These are the problem-solving interference. Interference occurs when two or more waves. These are some summary points. Now, the Michelson interferometer. The Michelson interferometer is centered around a beam splitter which transmits about half the light hitting it and reflect the rest. It can be very sensitive measure of length. Now, this is all for this lecture. Thank you. Thank you all.